Okay, so yeah, let's start. So we have two more classes, today's class and one more class, and it's good enough. I just checked that we can cover whatever we wanted to cover. So today we will, so we had proved in the last class Dirichlet unit theorem for S units, and now what we want to do is Minkowski's bound. So today we will do some preparatory stuff, and in the last class we should be able to do it. Okay, so I will start sharing the screen. You can just confirm that you can see the slides.
Yes, sir.
Okay, good. So we will discuss some basic things about lattice points and some volume computation, and we will use these to do Minkowski's bound in the next class. Okay, so let's start. So there's a concept of fundamental domain of a lattice. So suppose psi1, psi-n, psi1, psi2, etc., psi-n are vectors in Euclidean n space, and assume they are linearly independent, and then the abelian group generated by them is a lattice. So a lattice is a discrete subgroup. Okay, so mostly we will take it with the same dimension. So the abelian group generated by them is a lattice, and a fundamental domain for this is for this lattice is any measurable set in Rn such that every vector of Rn is congruent to a point from, so a fundamental domain is a set, let us say F, and if you take any point in Rn, modulo the lattice, it is congruent to a point from this set F. Okay, so every point in Rn is congruent to a point in this set, modulo your lattice, and exactly one point. Okay, so fundamental domain has two properties. Everything is congruent to something from here, and there's only one representative. There cannot be more than one representative for a point. Okay, so everything is congruent to exactly one vector in the set modulo the lattice. Okay, so we can take it to be, this will be the standard thing to do. You can take the linear combinations T1 xi1 plus etc. plus Tn xin, where the Ti is varying between 0 and 1, including 0 and excluding 1, so that repetitions will not come. Okay, so you can think of, I mean, in real line, if you take integers as the lattice, then of course closed at 0, open at 1, that is this set. If you take a lattice generated by two complex numbers W1 and W2, ZW1 plus ZW2, then modulo that thing will be T1W1 plus T2W2, where T1 is between 0 and 1, T2 is between 0 and 1. So usual, if you take 1 and I, then this is nothing but the unit square with two sides removed. Okay, so this is a fundamental domain. Now let's do a volume computation. So let A be an ideal of the ring of integers of this number field. And we are going to view it as a lattice in Rn. Rn is what? Rn is a product of completions at the Archimedean primes, at the Archimedean absolute values. So our standard notation, number of real embeddings is called R1, and number of complex embeddings is twice R2. R2 is half the number of complex embeddings. Then N is R1 plus 2R2. And this ideal in OK, you can view it as a lattice in Rn. Right? And let F be a fundamental domain of A. And then we want to do what is its volume, and volume is in terms of the discriminant. So this is the discriminant of A, modulus square root and 2 power minus R2. And this is same as 2 power minus R2 times norm of this ideal A times square root of the discriminant of K. So what is this notation? Discriminant K? Discriminant K meaning discriminant K over Q of OK, the ring of integers. Okay, so why are these two are equalities? We know because we have for any fractional ideal B, we have done long back that discriminant of B and discriminant of OK are they differ by square of the norm of B. So that gives you this equality. This equality follows from that, because if you square this is discriminant of A, that is norm A squared times discriminant of OK. This is the notation for discriminant of OK. So notation dk stands for discriminant of OK, and n denotes norm from K to Q, norm of an ideal. Okay, so we just need to show the first equality, second one is automatic. So let us do this. So you remember discriminant, right? You take a basis. So what is discriminant of an ideal or discriminant of a fractional ideal? What we defined is discriminant for a set of, so if K over Q is dimension n, what we have defined as discriminant of a set of n vectors. If they are linearly dependent, it will be 0. If they are linearly independent, it will be non-zero. And so what is discriminant of an ideal? We defined it as discriminant of various bases you take with basis elements, the elements of the tuple from the fractional ideal, and you take the ideal generated by all these discriminants. That's how we define the discriminant. But here it's easier because Z is a PID. It will be a free module, and therefore you can take a basis and take the discriminant. Okay, it's easier here. Anyway, so the ideal A has a basis alpha 1 etc. alpha n over Z, because finitely generated we know of Noetherian because it's Noetherian, and then it is free because Z is a PID. So take a basis and let sigma 1 etc. sigma R1 be the real embeddings, and tau 1 etc. tau R2 and their conjugates tau 1 bar tau 2 bar etc. be the complex embeddings, and then you can map alpha to all these embeddings, sigma 1 alpha etc. And what is the discriminant? Okay, let's also write tau j alpha as xj plus iyj, right? These are the complex embeddings. So xj and yj are real numbers. So tau j alpha v we will write as xjv plus iyjv. Now there's nothing much here. This just follows from the definition of the discriminant and definition of volume. So discriminant of A is the square of the determinant of an n by n matrix. And what are the entries of this n by n matrix? The first R1 rows are given by sigma I alpha j, the real embeddings. Next R2 rows are given by xij plus iyij as j varying from 1 to n. Because these are the complex embeddings, and the next R2 are the conjugates of these complex embeddings. So next R2 are given by this. So you take this n by n matrix and take its determinant, take its square. This is the discriminant. Now, you know what you do is addition, and it's easy because xij plus iyj is there in one row. Correspondingly, R2 steps later, you have xij minus iyj. So you can add those two and get 2 xij. Okay, and similarly, you can do one more operation. You can do some elementary row operations, and you can show that up to a sign, this is 2 power 2 R2 times the square of the determinant of the n by n matrix, consisting of first R1 rows, no change. Next R2 rows are given by xij. What you have done is you added this to that, so you would have got a 2 xij, 2 comes out. Okay, R2 many times 2 comes out, and then once more 2 will come out from the next R2 rows are given by yij. These are just elementary operations, and you know how to compute the determinant under elementary operations. So you get this. The latter is the square of the volume of F. You know this. The volume is given by a determinant formula. It's the most basic example is this, and more generally the same formula holds. Area of a parallelogram obtained from two complex numbers a plus id and c plus id, and the origin is the determinant of abcd, ad minus bc. So it's exactly that. So when you put it in this shape, the volume is the square of the volume is exactly this determinant. So you've got your formula up to a sign, and sign doesn't matter because you are taking modulus. So you wanted to show this. So what you are getting is 2 power 2r2 times this, the square of the determinant is square of the volume. So you take square root. Right? Discriminant is square of that determinant, right? Yeah, so maybe what I have written, there's a slight typo. I am taking square of this determinant, which is the discriminant, and yeah, maybe there's a small change here in taking the square. Anyway, you can just check this. Okay, if there's a correction to be made, I will make it in the slides. But there's nothing much. It's just, you know, the formula for the volume, and the corresponding determinant will give you the discriminant. Yeah, correct. No, there's no mistake. We had the square of the volume, and we had the square of the volume equal to the discriminant. So volume is square root of the discriminant. There's no problem. And 2 power 2 R2 gave you 2 power R2. So this is fine. So that's a proof. So this is okay. And this we will need to use in the next class. And let us do one more thing. So we want to show that certain sets will contain a lattice point. So we basically want to say that if a set is big enough, a measurable set is big enough, then it will contain lattice points. This is the exact claim. Let L be a lattice of dimension n in Rn, and let F be a fundamental domain of its lattice, of this lattice, and let C be a subset of Rn, measurable subset of Rn, and assume these three conditions, that it is closed, it is convex. What is convex? Any line joining any 2 points is strictly inside, and symmetric, meaning symmetric around the origin. If Z is there in your set, then minus Z is also there. Okay, assume C has these three properties, and suppose it is big enough. C is big enough in this sense. Volume of C is bigger than or equal to 2 power n volume of F. Then the claim is that there is at least one non-zero lattice point in C. Okay, so lattice is like, you know, a grid, right? A Z grid, or, you know, it may be a parallelopiped, is that the word? Parallelepiped, whatever. So it's that kind of an integer grid. That's what a lattice is. And you want to say, assert that your set certainly has at least one non-zero lattice point. And if it's big enough, right? If it's big enough, you will assume it will happen. And this is the inequality which will guarantee it. So let's prove this. So we are going to prove this assertion with strictly bigger than, that is step 1, and step 2 will be making use of that. So let us assume that volume is strictly bigger than 2 power n times volume of F. Now, F is a fundamental domain, right? What does that mean? Any point here, modulo L belongs to F, and uniquely. So it's a disjoint union. Right? Any point belongs to this union. That is first condition, and it belongs to a vector in a unique fashion. So that's how you get the disjointness. So this is the definition of the fundamental domain, as X varies in the lattice. And now, you know, C is your set. You take half C, meaning half X, where X belongs to C, and you intersect with this union. So you will get disjoint union of half C intersection translates of your fundamental domain. Okay.
But what is C being symmetric mean?
If Z is a point in C, then minus Z is also in C.
Okay.
Symmetric around the origin.
Yes.
Okay. And convex, you know, and closed, you know. We will see in the next slide, all this will be used. So this is okay. This is a disjoint union of this. And therefore half C is a disjoint union of half C intersected with all these translates of F. Okay. Now, because it's a disjoint union, this is a measurable set. You can take the usual Lebesgue measure, which is translation invariant. What will be the measure of this? The volume of this will be summation of volume of these sets. Right? Over a disjoint union, you know, sum is additive. So volume of half C is summation of volume of this set. But what is volume of this set? Because of translation invariance, it is volume of half C minus X intersection F. Okay. Now you use the condition that is given. What is the condition that is given to you? Volume of C is strictly bigger than 2 power n volume F. What can you say about volume of half C? Because you are in dimension n, this will be 1 by 2 power n volume of C. And 1 by 2 power n volume of C is bigger than 2 power n volume of F. So 1 by 2 power n volume of C is strictly bigger than volume of F. So what you have here is, this is strictly bigger than volume of F. So what can you conclude? So you can conclude that, suppose all these things were disjoint. As X varies, if these sets were disjoint, then sum of the volume will be the volume of the union of these things, but everything is contained in F. So it will be at most volume of F, less than or equal to volume of F, if all these things were disjoint. But the condition that is given to you is this is strictly bigger than volume of F. Therefore, you conclude that these are not disjoint. These sets are not disjoint as X varies. So since the volume is strictly bigger by our assumption, and therefore you get that half C minus X intersection F. These sets as X varies in L cannot be disjoint. There has to be intersections, which means there exists Y1 and Y2 in C such that half Y1 minus X and half Y2 minus some other X, they should be equal. There exists X1 and X2 not equal such that there exists Y1 and Y2 such that half Y1 plus X1 is half Y2 plus X2 for suitable X1 and X2 in L, and X1 not equal to X2. There exist two such things which meet, and therefore you get a common point like this. Okay. So what does this mean? This means half Y1 minus half Y2, X1 and X2 is in the lattice. That's an additive group. So half Y1 minus half Y2 is X2 minus X1, which is in L. So you get half Y1 minus half Y2 belongs to L, and this is non-zero, right? Because X1 not equal to X2, Y1 is not equal to Y2. So you get a non-zero element in L. What is our aim? Our aim is to show that your set C contains a non-zero lattice point, and this is a non-zero lattice point, and we claim that this belongs to C. Why does this belong to C?
Because it is symmetric.
Yeah, because it is symmetric and because it is convex, both. Because Y2 is there, minus Y2 is there, and half Y1 plus half minus 2 is the midpoint of the line joining, so that is also there. So this is in C because by symmetry minus Y2 is there, and by convexity the midpoint is also there. So you have a non-zero lattice point in C. So that's what you wanted to show. Now suppose you don't have a strict inequality, you have only greater than or equal to, then we can do by step 1, you take a positive epsilon and take 1 plus epsilon times C, so slightly bigger than C. So volume is strictly bigger than volume of C, because what comes out is 1 plus epsilon power n, which is strictly bigger than 1. And that is given to be bigger than or equal to C. Therefore by step 1, what do you know? 1 plus epsilon C contains a non-zero lattice point. So by step 1, there is a non-zero lattice point in 1 plus epsilon times C. Now take epsilon going to 0. So because C is closed, you can conclude that one of these lattice points has to be in C itself. Not all these, for every 1 plus epsilon C, if lattice points are outside C, then there is a problem, and that is because C is closed. Okay, so existence of lattice points is done. All these I am doing today so that in the Minkowski bound proof we will need this. Okay, so maybe we don't have much to do today. We are going to do one more volume computation. That's all that we need to do. So this is our standard notation. N is R1 plus 2 R2, and Rn is product of completion V in S infinity. Why is that? Because R1 many times R is coming, and R2 many times C is coming. R2 many times C is coming. So the dimension over R will be 2R2 plus R1, which is N. Okay. So, right, because if you have a complex embedding, that embedding and its conjugate gives you the same absolute value. So V doesn't change for a complex embedding and its conjugate. Therefore, this is correct. So here this set has, what is the cardinality of S infinity? V is absolute value. So the cardinality of this is R1 plus R2. R1 is real embedding, R2 is half the number of complex embedding, and this cardinality is R1 plus R2, and therefore this dimension is R1 plus 2R2. Now we are going to do, some basic integration. So for each A positive, you consider the convex region determined by summation NV mod ZV less than or equal to A. The tuple ZV such that this is true. What is NV? NV is 1 if V is a real embedding and NV is 2 if V is a complex embedding. And we claim that its volume, the volume of this convex region is given by this formula. So if A is a positive number, if you take this convex region, then its volume is denoted by V R1, R2 of A, and it is given explicitly by this formula: 2 power R1, 4 power minus R2, 2 pi power R2, 1 by n factorial A power n. This is the claim, and this is not difficult. It's a simple integration. Without loss of generality, we can take A to be 1. Why is that? Because you can check from this that V R1, R2 of A is A power n times V R1, R2 of 1. It's just scaling, and therefore it's enough to compute this one. You have to compute that VR1 R2 of 1 equal to this much without A power n. That's what we will do. So it's just dx dy equal to r dr d theta. Change it to polar coordinates and you know the change of variable formula. The Jacobian of the transformation is just r for one variable and for many variables similarly. So each ZV you express in polar coordinates as uv exponential of I theta v, where theta v is between 0 and 2 pi and uv is positive. And then v r1 r2 1. So you have got this region, right? This convex region you have. So this is what? This is mod z1 plus etc. mod z2 plus etc. mod zr1 plus 2 mod z r1 plus 1 plus etc. Twice the rest of this thing less than or equal to 1. So the integration is over that region. Mod u1 plus mod u r1 plus 2u r1 plus 1, because exponential anyway modulus is 1. So 2u r1 plus 1 plus etc. 2u r1 plus r2 less than or equal to 1. Over that you have to integrate what? You have to integrate u r1 plus 1 up to u r1 plus r2 and all the other things, du1 and d theta. Agree? Area is, volume is given by integral over the region. And this ui's are coming because of dx dy is r dr d theta. Original integral would have been just the du dz, but you are doing the polar coordinates, so each dz is r dr d theta. Okay, so you have got for the complex embeddings corresponding to that, you have this ui's coming, and then you have the dx's, and then you have the d thetas. Okay, so this is the integral that we have to do. We can restrict ui to be positive even here. What will happen is you will have to multiply by 2 every time. So finally you will have to multiply by 2 power r1. So we will restrict ui to be positive. Whatever you get, you have to multiply by 2 power r1 in order to get the final answer. And the d thetas you can take out, right? I mean, you can take out in the sense that is independent of, this is independent of the d thetas. So each d theta will contribute 2 pi. And how many d thetas are there? R2 d theta. So each d thetas together will contribute 2 pi power R2. That's also obvious. Now we are going to make the change of variable. Each of this twice this, you call it W. 2u R2, 2ui you call wi for these things. So what will happen? dw will be 2 du. So each of the du will be half dw and u is also half w. So corresponding to each of this thing, 1 by 4 is coming out. So for R2 many times 1 by 4 has come, 1 by 2 from here and 1 by 2 from du. So 1 by 4 has come out. So 4 power minus R2 has come out. So all this is matching well. So you have 2 power R1 coming out because ui you have assumed positive. 4 power minus R2 came out because of that change of variable. 2 pi power R2 came out of all those d thetas. And then the remaining thing is WR1R21, where WR1R2B is this integral over u and du's. There's no d theta because all of them have come out. and there's no difference between real and complex because of our change of variable w equal to 2u. And where are you integrating? This is over the region. There's no condition now. All the ui's are positive, and u1 plus etc. plus u r1 plus r2 is less than or equal to b. This is, x plus y less than or equal to b, that kind of a thing in more variables. All the ui's are positive. As earlier, this is same as at 1 b power n comes out, right? It's scaling by b. And we need to show that w r1 r2 of 1 equal to, what should we show? Because if you recall, our claim is, so all these things have come out already. A power n anyway is, we are not bothered because we are computing at 1. So what you need to show is w r1 r2 at 1 is equal to 1 by n factorial. That integral is 1 by n factorial. We have to show that this is 1 by n factorial. It's a beautiful trick, right? So you have this kind of a multi-integral and the answer is 1 by capital N factorial, and it's very easy. Okay, so let's do it. So what you need to remember is, suppose you have integral of the region x plus y less than or equal to 1. That is a triangle, right? And that's a double integral over that triangle. And the standard thing that you do in calculus, fix one variable and the other you write as 1 minus x. So x plus y less than or equal to 1 is same as y less than or equal to 1 minus x, and y x you can vary from 0 to 1 and y you will vary from 0 to 1 minus x. Same trick you can do here. So that is this trick. So w r1 r2 1 is over that region. I have taken, the variable u1 I have brought to the other side. So the remaining thing will be w r1 minus 1, because u1 is from this r1 many things that has gone to the other side. So it will be w r1 minus 1 comma r2 of 1 minus u1 du1, varying from 0 to 1. If you plug in, you will see. If you plug in this thing to this, the definition of this, you will get this integral. So this is just the standard thing that you do in calculus. If you want to integrate on x plus y less than or equal to 1, you integrate one variable going from 0 to 1 and the other variable going from 0 to 1 minus x. Same trick. And this one, because w r1 r2 of b is b power n. Dilation is b power n comes out and the remaining is 1. So when you have this function on 1 minus u1, 1 minus u1 power the dimension, because it is r1 minus 1 plus 2r2, it is n minus 1. That is there here, and times this of 1, which is a constant which has come out. So it is just integral 0 to 1, 1 minus u1 power n minus 1 du1, and this integral is one variable integral. You check, the answer is 1 by n. So you have got w r1 r2 at 1 as 1 by n w r1 minus 1 r2 of 1. So you can do induction. You can do induction, and induction will tell you, you can repeat the steps up to this r1 goes away. So up to 0 comma r2 of 1 you can do that. You will get n times n minus 1 every time the dimension 1 by the dimension is coming, and that will be n minus 1 etc. n minus r1 plus 1. So you got this. Now we have to compute w0 r2 1. Same trick. w0 r2 1 is w0 r2 minus 1 at 1. Integral will be t1 times 1 minus t1 power this, because now there is a variable u also. It is r dr d theta, and that r is coming. Therefore, there is a slight change here. It is exactly this, and this you can integrate and see. You will get 1 by 2r2 times 2r2 minus 1 times this. So you can apply induction. So by induction, you will get this to be 1 by 2r2 factorial. So what is coming here is, this is 1 by 2r2 factorial. But the whole thing together is then n factorial, right? Because what is this? N is r1 plus 2r2. So this is 2r2 plus 1. And what is remaining is 2r2 factorial. So 2r2 factorial times up to n. So everything is continuous. So it is n factorial. So wr1 r2 at 1 is 1 by n factorial. Okay, so that's all that I wanted to put in the lectures today, because Minkowski's bound is all that is remaining, and that we will do in the next lecture. So today's was a very quick lecture, and so some simple computations, but very beautiful. Okay, and all this we will use and do Finiteness of class number we discussed in one class. I don't think I will repeat it because we are going to do slightly better. We are going to give not just finiteness but this Minkowski's bound. Okay, so that let us do in the next class. And possibly I would like to do, I mean, if possible, I would like to do Hermite's theorem also. Hermite or Hermite or whatever, Hermite's theorem. But I'm not 100% sure about it. Anyway, let me stop the recording here. Let me stop the recording. And